fingerprinting was helpful in answering. Namely, if you ask two hosts for their clocks and compute the time skew, are they the same hardware clock? So this is useful when you need to tell two devices that might be one virtualized physical device from each other. And also, this is probably going to be very useful in mapping the clouds, which are all virtualized platforms. But so we haven't seen any people exploring that, but that's definitely something that's going to come up. And it turned out that the clock skews were so consistent that even the network latency could be diffuted with some proper statistics. And this is what the real-world clock skews from their paper, measured on a cluster of desktops, looked like. So you see the hosts ordered by the, okay, help me out here.
By the lowest skew they measured within 12 hours.
So they are arranged by the lowest skew measured within 12 hours, and the height of the bar is the deviation over that time that they observed. Because, of course, the clock skew itself varies a little bit based on things like the temperature, possibly, or maybe power consumption, or maybe any one of those things that you can imagine can affect the physical clock. So the clock skew itself is subject to variation. But even so, you can definitely tell one of the computers on the left from one of the computers on the right. And so, you know, come 2008, we were thinking, well, beacon frames are transmitted 10 times a second, and they have this microsecond clock, and that clock is on the RF interfaces chip. So it's the crystal on the actual card. And this is great because we can just sit there and listen, and we can try to fingerprint the APs. And we said that that's what we're going to do during our talk on fingerprinting access points by throwing garbage frames at them. And guess what? A couple of weeks later, we see this paper by Jana and Casera, published in the scientific conference Mobicom, and it's called "On Fast and Accurate Detection: Unauthorized Wireless Access Points Using Clock Skews." And I go like, darn, scooped. Anyhow, but we start reading this paper, and it turns out that, you know, yeah, they can tell an access point from another access point. Presumably, they can tell an access point that is your laptop with one of those cards that let you go into master mode. But they say, this is really good. This is really fast and accurate, and this is really hard to spoof. Here is the timestamp in the beacon. This is what, you know, you'd be able to see it in its 64-bit glory. You know, if you could do that sort of thing, it could be useful, because imagine most of the time you've got a situation when you come in, you open up your laptop, you see some beacons, and the access point that you start dealing with based on what you see in these beacons, even if you do the crypto authentication, that's actually an evil twin kind of a laptop. And you think that crypto protects you, but not so. Crypto is complex, parsing complex data is hard. You start parsing complex data way before you can do any meaningful crypto, and this is your owning a MacBook in 60 seconds talk by Jenny Cash and David Maynard, and then the month of kernel bugs, and there is no driver out there that can be completely relied on to accept complex data and not screw up when parsing it. So wouldn't it be nice to fingerprint a rogue access point before you start interacting with it. And we can explain this by drawing a picture with the access points and the log attacker laptop. But let's not do that. Let's go for something more dramatic. Let's have a Star Wars analogy. So here's your station, and we're looking to associate with one of those access points. Yes, and all of those little access points out there. And one of them is actually a log access point. Could you hold this is the Imperial March, if you can hear it. Right. And sooner than you know, you're within the tractor beam and you're being served with a nice little layer 2 kernel exploit. And, this is no moon, not really. And the access point goes to that. So, well, thank you. That's enough Star Wars for now. So the idea is then you could use fingerprinting of the access point by timestamps or by any other means, really, before you start accepting more complex data, more complex frames from it, by observing that this thing has a happy clock inside, and it's actually broadcasting that clock. And what you can do is you can just see that it's not the Tatooine that you're looking for, but instead something completely different, a small moon maybe, and desist from approaching any closer. So how can you do that? You can do that by observing that there is a timer on the card, and you can query that timer in your card for the very accurate time stamping of what you're getting, of the frames that you're capturing, beacon frames included. And the reason for that timer, and this is 64-bit and microsecond resolution, is that the clients adjust their timer from this beacon timer to stay in sync with the AP. And the collision of rodents being such a delicate dance with the virtual carrier sensing and all that, that they need to do this. And so your RF chipset actually knows how to synchronize your clock with an external clock. And so we have a high precision set of timestamps to go by. And this is a known fact. And so coming back to this paper that offered the fingerprinting mechanism, they observed that these are approximately the clock skews that you expect to find on your Linksys and your Netgears. We mostly use Arubas at Dartmouth, but the picture looks the same. And so you've got clock skews on the order of maybe 64 to maybe 10 parts per million. And these, of course, vary normally because the clock on the access point itself varies, even its skew varies, and the variation is 0.30, 0.70, so less than 1 part per million. And the clock skews themselves are on the order of 10 to 60, so you can actually measure it quite accurately, and you can be sure that it stays within the same region. The error of measurement is not really that large. Okay. And the conclusion that the paper, a very nice paper, and I urge you to read it if you're interested in this, the conclusion was that spoofing this was very hard. A microsecond clock is a lot better than what you get on your laptop. Microsecond level events are much better than